We're starting chapter 13, which is about experiments and observational studies. We're going to first talk about observational studies. So an observational study is where researchers observe responses, but they don't assign them. They just watch what happens, or they look at the data, but they didn't ask any questions and they didn't apply any treatments. This is good for discovering trends and possible relationships. There are two different types of observational studies. The first is a retrospective study, where researchers first identify subjects and then look at past data and responses, or they look at the history. The issue with retrospective study is that it's based off of historical data, and that data can have errors. It's not something that you've done. You're relying on somebody else's work. The other type is a prospective study. This is where you choose the subjects in advance, and then you collect the data as the events unfold. Observational studies are great for telling us if there is an association between two variables. However, they cannot give us a cause and effect relationship, and they cannot give a generalization of the population. They're not random, so it doesn't necessarily represent the whole population. For example, a recent medical study showed that of men who have had a heart attack, those with a certain protein are more likely to have a second. Now, there's a couple of different conclusions that we could try and leap to here. We could say, oh, this protein is going to cause the heart attack. Or we could say, oh, this heart attack is causing the protein, which then will lead to another heart attack. But we can't actually make that leap because there could be a lurking variable that causes both, and they could just be completely unrelated. We don't know what it is. We just are kind of showing that there might be some association there. This leads us to experiments and samples. Both experiments and samples use randomization, unlike observational studies. They just use it in different ways. Samples are taken from a population at random and are used to try and represent the whole population. Experiments may not take their experimental units at random, but they pick who gets what treatment randomly. Experiments can draw stronger conclusions in sample surveys, and that's because in an experiment, you're actually applying different treatments, and then you're observing what happens. So an experiment is able to kind of go to a cause and effect relationship where a survey is not. What we do is we look at the differences across the treatment groups in experiments to cancel out bias. So each group may be biased, but they're going to be biased in the same way. This is because you chose who goes into what treatment group randomly. So because randomization was still used, it's okay if there's bias because each group would then be biased the same way. How does the difference make a difference? So different groups are going to have different means, averages, even if the treatment has no effect. Randomization causes the means to differ, at least slightly. So how big does a difference have to be to show that the treatment was effective? If the differences are larger than we would assume to get from just the randomization, then we can attribute the differences to the treatment. So essentially, if it's bigger than what you expect, you're good to go. These differences are called to be statistically significant. Now, we will learn later on in this course how to actually determine if something is statistically significant, but for now, we can just kind of look at it and say that the difference was bigger than maybe what was expected, and then as a result, that means the treatment works. So how do you know when the difference is big enough? Again, it just has to be more than what you expect. So let's take a coin, for example. If you flip a coin 100 times, you would expect to get heads 50% of the time, which means you would end up with 50 heads and 50 tails. If you got 54 heads, that would be okay. That seems to be within the right range. We expect there to be some differences. It doesn't always work out perfectly. However, if you were to flip a coin and 94 of the 100 times that you flipped it, you ended up with a head, you probably had some type of outside influence, and that would be statistically significant. That would be saying, okay, this coin, not fair. All right, I want to look at a couple of examples that I stole from Khan Academy. We're actually going to do this task in class tomorrow, so you may get lucky and you may see a couple of these examples again, which will make the task easier for you. But we're going to identify what type of statistical study was used. Was it an experiment, a sample survey, or an observational study? And then we're going to look at the type of conclusions we can draw from it. That's kind of why I just talked about the statistical significance a little bit, even though it was kind of out of place. So our first example, and I struggled with my animation, so the answer already popped up, but that's okay. Roy's Toys received a shipment of 100,000 rubber ducks from the factory. The factory couldn't promise that all rubber ducks are in perfect form, but they promised that the percentage of defective toys won't exceed 5%. Roy wanted to get an estimation of the percentage of defective toys, and since he couldn't go over the entire 100,000 ducks, he took a random sample of 10 ducks and found that 10% of them were defective. This was a survey. It's a survey because there was randomization used, but he didn't apply any type of a treatment to it. He just took them and determined if they were defective or not. So that makes it a survey. He surveyed those 10 ducks. So is this study appropriate to the statistical questions it's supposed to answer? And no, the sample was too small. Now the sample size doesn't have to be huge, but 10 out of 10,000 or 100,000 just isn't going to be enough. So we'd need a bigger sample to be able to come to any type of conclusion here. For our next example, a nutritionist had a hypothesis that eating a single banana an hour before a marathon can improve performance and reduce running time. To test her hypothesis, she randomly assigned a group of 360 men to participate in a marathon in two groups. One group was instructed to eat a single banana an hour before the race. The other group was instructed to eat nothing during the few hours before the race. After the race was done, she compared the average running times of the two groups. This is an experiment. Randomization was used not to pick the people. She's picking people who are running a marathon, but she randomly decided who would go into what group. So that makes it an experiment because she also forced one group to eat a banana and one group to eat nothing. So she ended up finding out that the average running time of the group who ate the banana was 5 minutes shorter than the running time of the group who hadn't. So we want to know what valid conclusions can be made from this result. The results here suggest that male runners will likely run a faster marathon if he eats a banana an hour before the race as opposed to eating nothing. Now there are a lot of issues here. The first is that we can only talk about male runners because she did not include female runners. The other thing is that the other group ate nothing, and then the first group only ate a banana. So perhaps having something to eat also helps as opposed to having nothing to eat. So we'd have to do a little bit more with this experiment probably, but we can at this point conclude that eating a banana is better than eating nothing. Let's look at another example. Alma has developed a new kind of antibiotic. For the antibiotic to be sufficiently effective, it has to kill at least 90% of bacteria when applied to harmful bacteria culture. She applied her antibiotic to a petri dish full of harmful bacteria, waited for it to take effect, and then tried to estimate the percentage of dead bacteria in it. She took a random sample of 300 bacteria and found that 94% were dead. Then she calculated the margin of error and found that the true percentage of dead bacteria is most likely to be above 90%. This is a sample study. The reason why this is a sample study is because, again, there was no other type of control or treatment group. She just looked at the one. We want to know, is this study appropriate for the statistical questions it's supposed to answer? And in this case, no, it's not, because she shouldn't have done a sample study. She should have done an experiment and should have had different treatment groups and at the very least a control group, and she did not have that here. So let's look at our last example. Our last example says the mayor of Statsville has decided to allocate her education budget between the two high schools in the town, Stat Sticks and Datum High. To decide what school deserves a bigger proportion of the budget, she went over the grade sheets of the students from both schools in the past 5 years and analyzed the data. Because she's just looking at the data, she's not applying any treatments, she's not doing any random allocation, she's just taking the data from the past 5 years and analyzing it. This is an observational study. To be specific, it is a retrospective study because she's looking at past data. She ended up finding out that the overall grade average for the Stat Stick students is 5 points higher than the overall grade average of the students at Datum High. So, what valid conclusions can be made from this? The only thing we can really say is that the students from Stat6 in the last 5 years had higher grades on average than students at Datum High. She only looked at the past 5 years of data, so we can only judge off of those past 5 years. We can't say overall all students always at Stat6 High have better grades. We can't say that Stat6 is a better school. All we can say is that in the past 5 years, their students have higher grades on average than the students at Datum High. Okay, that is it for tonight. We're going to keep practicing identifying what type of statistical study was used, as well as what conclusions we can make and the validity of the study in class tomorrow. But that is it. So have a good night. I'll see you tomorrow.